Hello, everyone, and welcome to the last day of chemistry. So we're going to wrap up the semester by talking about fission and fusion. So these are going to be two different processes of which we can undergo massive changes of nuclei. So one of the first things we have to figure out is what causes essentially nuclei to stay together, and where is the energy going to come from when we change the nuclei? So to start, we need to remember that nuclei are essentially held together by balance in between attractive forces. So these are called the strong nuclear forces. And they're based on the idea that nuclei like other nuclei. So protons and neutrons all attract each other. However, it turns out that electromagnetic forces tend to push nuclei apart. Because again, as I start putting in protons, all those protons kind of hate each other. And so I need to have that buffer of neutrons to help counteract. And so generally what we tend to see is as a nuclei gets bigger and bigger and bigger, I'm going to have both more strong forces holding the system together and more electromagnetic forces pushing everybody apart. But the question is, who wins out? Well, there's a couple important things to keep in mind. Strong nuclear forces tend to work at very short distances. Electromagnetic tends to dominate at longer ones. So as you might expect, as nuclei get bigger, we tend to see them become a little less stable as electromagnetic forces become more important. But in terms of numerics, we can actually evaluate this stability by looking at the amount of energy that's formed when I start trying to form various nuclei. And the way we can do this is by looking at what's called binding energy. So if I was going to make deuterium, I can go ahead and do that by combining one proton with one neutron. And then, ta-da, I've got deuterium and a whole bunch of energy. Any energy released means that my new atom is that much more stable. And so this tells us a lot about the stability of the system. So now I need to find a good way to determine exactly how much energy is released. Now, it turns out when you start releasing energy on the scales of a nuclear reaction, it turns out that any energy produced corresponds to a reduction in mass. Now, this might seem a little bit odd. I can't just produce energy out of nowhere, and I can't just consume mass. However, turns out Einstein had an equation for that. So this is the origin of that famous E equals mc squared. You can go ahead and produce or consume mass, but it has to be accompanied with a corresponding change in energy. If I consume mass, I produce energy. If I produce mass, I have to consume energy. And it turns out, since the conversion factor is the square of the speed of light, it turns out it's a lot of energy. So what we can do is take a look at the amount of energy released. So again, negative sign here. For a reduction in mass, negative sign here, so everybody should be just fine. And by measuring the change in mass of, say, the initial mass of my proton and neutron and the final mass of my new deuterium molecule, I can go ahead and figure out exactly how much energy is released without actually having to measure it, which is quite nice because some of these experiments would be quite catastrophic. So one of the first things we can do is try and figure out what the conversion is in between energy and a change in mass. So what we can do is say, I have a unit of one atomic mass, which I can then turn into kilograms, and then multiply that by the square root of the speed of light. So here's my E equals mc squared term. However, when I do that, that gets me units of kilograms meter squared per second squared. Well, it turns out this is the same thing as 1 joule. Now, you can produce these energies in joules, but it turns out it's a really big number. So it's a little bit more convenient to turn it into electron volts. So again, an electron volt would be how much energy or how much volts would I have to give to a single electron. So it turns out that if I have a change of mass of 1 atomic mass unit, this would produce about 9 times 10 to the 8th electron volts. That's a little bit messy. So we can just report this as 931 mega electron volts per change of atomic mass unit. Now I can go ahead and apply this to a real system. we can try and figure out the binding energy of helium, which is one of the most common isotopes. I mean, this is our alpha particle. And so we can do this by calculating the total mass of summing up all of your protons and all your neutrons. It's about 4.03 atomic mass units. And you'll note that helium is only slightly less in mass. We don't see a difference in mass until we get to that 0.03 unit. So again, doesn't feel like it's that big of a difference in mass. However, when I multiply this by 931 mega electron volts, it turns out that the binding energy for helium is a little under 30 mega electron volts. That's a lot of energy. I mean, an astonishing amount of energy is produced if I was going to make helium this way. However, to keep it easier to compare the binding energy of different nuclei of different sizes, we often end up expressing this binding energy as per nucleon. So we add up the total number of nucleons, so that's protons plus neutrons, and we take that mass and divide it by the nucleons. So it turns out that this is about 7 mega electron volts per nucleon, which is still a lot. Now, when we've got these essentially binding energies for each of our atoms, we can go ahead and try and figure out which nuclei are going to be more favorable or less favorable on, again, a per nucleon level, which makes everybody a little bit more directly comparable. So it turns out we have the most stable nuclei around a mass of about 60. So this would be elements somewhere around nickel or iron. And it turns out that any element lower than this, I can go ahead and combine multiple nuclei to make a more favorable species. However, it is, for example, I could combine 3 heliums to make 1 carbon, and that's a very favorable species. Or I could put 4 of them together to make oxygen, or 5 to make neon, and I get this big increase in stability each time I go. However, due to some nuances of magic numbers and unfavorable combinations, it turns out that not every species will be equally favorable. So for example, beryllium is actually a very bad structure to try and have. It's fairly unstable, and one of the reasons why you don't tend to see it much in nature. Nitrogen is a little bit less stable, and turns out so is fluorine. So again, we have these big islands of stability around helium, carbon, oxygen, and neon. So not too surprisingly, they occur quite a lot in nature. If we go ahead and look on the other side, as elements get higher and higher masses, it turns out that they become less and less stable. And so, if you're looking at, mass numbers of 120, so this would be somewhere around 10, you're not gaining too much energy if you break apart. However, once you get to a certain point, your nuclei are already pretty much ready to fall apart, and it will be a lot more favorable if they can break apart to form lower mass species like iron. And so this idea of combining nuclei to get more stable species is called fusion, and this idea of breaking apart heavy nuclei to gain more energy is called fission. And it turns out that everybody pretty much wants to become about iron because it's very stable. So let's go ahead and look at the 2 ways we can make iron. So it turns out if I get to really high temperatures, so I'm essentially overcoming any sort of transition states or kinetic barriers, it turns out I can get nuclei to essentially come together. So the classic combination is I can take 2 hydrogen atoms, smash them together, and make deuterium, and then add in releasing a positron, and then bring in a 3rd proton, and then I make helium, and then I can go ahead and rearrange to make a stable helium-4 atom. It turns out that this process ends up occurring fairly readily at a temperature above 14 million Kelvin. So a little bit hard to do on Earth. However, this is essentially how stellar masses go ahead and perform reactions to produce helium. And this tends to be the biggest energy producing reaction in our sun. It is very good at taking hydrogen, making helium, and then it takes all of these positrons and gamma rays that's produced along the way and uses them to essentially make a little bit lower frequency or higher wavelength light as they get absorbed and emitted in processes that we kind of referred to last semester. And so what we end up, as we go out on a sunny day, what you're essentially being hit with is all the photons that are left over from all of these various high energy fusion processes. It is worth noting that fusion bombs tend to use a very similar process where you have a whole bunch of hydrogen, you manage to use some sort of reaction to get it to very high temps, at which point it can go critical and start fusing to make helium and way too much high energy species. However, it is worth noting that artificial fusion, in order to try and control the level of the reaction, bring down the level of temperature needed, tends to try and start, instead of using hydrogen, so good old hydrogen, it tends to try and use deuterium and tritium, because this will produce a slightly higher energy yield with, much more importantly, a single step instead of this series of reaction cascades. However, one of the important things to note is that the world is not made of helium. So if I have a sun, what happens if it has a whole bunch of helium? Well, it turns out if the temperatures get past 100 million Kelvin, so these are going to be really hot stars, it actually becomes favorable to take 3 helium atoms and combine them together to make carbon. And this is one of the reasons why carbon is a fairly favorable species throughout the solar system. It turns out beryllium forms an unstable intermediate, so this becomes the real limiting intermediate. It's a high energy intermediate, so you need to make sure that this second reaction happens quickly after the first. And so it is worth noting, as you start increasing the temperatures further and further, it's possible to turn that carbon into oxygen with another helium atom. And then if a 5th one gets involved, you can make neon. And this can proceed so on and so forth until you essentially get to iron. So you can keep adding 2 protons in sequence till eventually you make iron. And this is one of the reasons why, if you look at the natural abundances of metals and species, you'll tend to find that even number elements are much more common than odd numbers. And again, the last endothermic process is iron. However, if you get to even higher temperatures, or to the temperatures involved in supernova, you can start performing endothermic processes, so processes that actually require additional energy, at which point you can start fusing iron to get all those post-iron elements. So it is worth noting that almost every element heavier than iron you find had its origins in a supernova. However, it turns out that these stellar fusion events aren't the only way you can produce elemental species. There's a lot of other elements that can be produced via what's called cosmic ray bombardment. So that our stellar mass ends up producing a whole bunch of extra nucleons. So as we've seen, fusion tends to produce a lot of proton byproducts, as well as a lot of other small atoms and nuclei, like helium or beryllium or carbon. Well, it turns out that these various nucleons, ranging from protons and neutrons all the way up, are released from the sun, where they can then hit our atmosphere and do some really fun things. One famous example is neutrons can hit the atmosphere and combine with nitrogen. So nitrogen 14 is the most common isotope of nitrogen in the atmosphere. And it turns out when it's hit by a neutron, that neutron can go ahead, kick off a proton off of my nitrogen and replace it with that neutron. So what I end up with is now carbon 14 and a free proton. That free proton will go off and do its things because I just made a hydrogen atom. But that C14, it turns out it's somewhat unstable. It has a half-life of about 5,700 years. And it turns out that that's what we do with carbon dating, because this carbon is then incorporated in all living matter at a very predictable rate, because plants will take it up in photosynthesis, and then that becomes sugars, and that becomes proteins, and everybody uses it. And it turns out that pretty much every single living organism has a steady level of C14. And once you stop exchanging carbon with the air, also known as you stop interacting with the air, which is not a good thing, it turns out that that level, that you no longer take up any more C14. So you can determine the amount of time at which you have ceased respirating to the current amount of time using the half-life of C14. And this is the major idea of carbon dating. So as long as the amount of cosmic rays hasn't changed tremendously in the last 10,000 years, you can use this to date species up to about 20,000 years. However, it turns out that there's a lot of other elements that can interact with neutrons from the environment. So one of the heaviest naturally occurring elements is U-238. In fact, it is the heaviest. And it turns out that it also can produce other elements when it's bombarded by high energy neutrons. Again, we need that high energy neutrons like we get from cosmic rays or artificial sources to overcome any kinetic barriers. However, U-238 can then temporarily make U-239. Turns out U-239 isn't that stable, so it will quickly break down via beta emission, so again, a high energy electron, to make neptunium. And this is how we get what are called transuranium elements or transuranic elements. So these are going to be any element heavier than uranium. The easiest way, you start bombarding with neutrons, but you can also bombard with any number of other low mass nuclei, whether it's bombarding americium with helium to make berkelium, or whether you're going to be adding something as heavy as a nitrogen atom. So shooting high energy nitrogen atoms at these transuranic elements. And each time you can get slightly higher and higher masses. So for example, you can take californium, react it with nitrogen and make, sorry, this is a typo. This one should be dubnium. And so each time you can get slightly higher and higher masses. So it is worth noting that current techniques have gotten us into every single element up to 118, or ognism, which was produced in Russia. And one of the questions is, how can we go ahead and start slamming together these high energy species? Well, it turns out that these tend to be done using what are called particle accelerators. So what you can do is take your precursor nuclei, whether it's uranium or just the simple nitrogen, and you can go ahead and, using oscillating electronic charges, drag that charged nuclei further and further up. And each time you put an attractive negative charge ahead of it, or a repulsive positive charge behind it, the atom keeps speeding up faster and faster and faster and faster until it gets to really high speeds where you can overcome any kinetic barriers. And so these accelerators have two major forms. One is a linear accelerator, where you send the charged nucleons under a straight line. And the other one is called a cyclotron, where you essentially send them in a spinning fashion until they get to a high enough speed that they can essentially undergo very fun fission events. So the most famous of these accelerators is the Large Hadron Collider, which is a little bit of a combination of a cyclotron and a linear accelerator, because it is a big circle, except for the fact it's a single circle and it's about 24 miles in circumference. So a little bit different set of scales. And it is worth noting that it's these accelerators that pretty much have produced all of your novel elements and particles. So you pretty much need either a linear accelerator or a cyclotron to make most of your transuranic elements. Also worth noting that a lot of these elements have a lot of uses in various levels of science. You can go ahead and use these for, say, radioactive tracers in medicine, or to or as tracers in biology to figure out exactly how, say, a radioactive nitrogen or fluorine in your PET scan moves through either a organism or through a whole ecosystem. However, one of the problems is that it turns out when you bombard a lot of nuclei with a neutron, it turns out you make it so unstable that bad things can happen. So one of these elements are called fissile, as they will break apart. And the most famous fissile material is uranium-235. So also, this is your radioactive or weapons grade uranium, because when uranium-235 is hit with a neutron, it turns into uranium-236, where it says, oh no, I don't like this, and immediately breaks apart into any number of species. One of the more common combinations is barium and krypton. And it also ends up producing 3 additional neutrons. And it's worth noting that this particular reaction will, in the form of gamma rays and high energy neutrons, produce about 82 gigajoules of energy. Yes, I know. Also, for you Back to the Future fans, this would be 82 gigajoules of energy. And this is the reason why the Doc needed uranium to power his DeLorean. It is that energy dense. There's nothing quite like it. However, one very noticeable thing is that this reaction requires 1 neutron, but it produces 3. This means that the reaction can sustain itself as it's producing the seeds for more reaction. And so what you can do is by adjusting the density of uranium, you can use that to control the rate. So essentially, by controlling the rate at which these neutrons will hit new uranium atoms. Thus, if you have a very dense or large sample of uranium, it reaches what is called a critical mass. However, if you go ahead and keep it below that critical mass in the subcritical range, you can keep the reaction working at a lower sustained level, and you have a nuclear reactor. However, it turns out that even if you're working with a material that isn't fissile, so it doesn't break apart, you can often end up producing radioactive isotopes upon exposure to neutrons. So a good example here is U-238, which we said previously you can make into U-239, and then under beta emission produces neptunium. So we've seen this reaction several times this before. However, this neptunium can then undergo a second beta emission to produce plutonium. Yes, that plutonium. It turns out that plutonium is fissile. So if you hit plutonium with an extra neutron, it can then break apart under a nuclear fission reaction, producing more neutrons. So it turns out that any isotope that itself isn't fissile but can produce these radioactive or fissile isotopes is called fertile. So you can take these fertile isotopes and make fissile material for either weapons or nuclear reactors in what's called a breeder reactor. And so plutonium is actually used in a fair number of nuclear power plants and is most famous as being the key element in Fat Man that was dropped over Nagasaki. So the second nuclear bomb dropped in World War II. And so one of the things is that it is worth noting that these reactors do allow a lot more different isotopes to be used as nuclear fuels, because you don't have to just use U-235. You can use this depleted uranium, so the remaining U-238, to make nuclear material. However, it is worth noting that they do tend to produce a lot more dangerous byproducts, a lot more hazardous waste, because the whole point of them is you're making radioactive and nuclear material. So I hope you've enjoyed the semester, and take care. Have a good break.